Section 9.1, Day 2. Alright, the first topic for today is called summation notation. So, first a little definition. We've got the sum of the first n terms of a sequence is represented by, so we're going to use this big Greek letter called sigma, which we use for sums. Notice we have a sum. We're going to be adding things up. And then on the bottom we're going to put I equals 1. So this number may change, but for now we're going to put 1. And on the top we're going to put n. And then to the right we're going to put a sub I. And this is going to equal, so we're going to be plugging in values for I from 1 up to n into our expression. So we're going to have a sub 1 plus, again, the sigma. Anytime you see that sigma, you know you want to add things up, plus a sub 2 plus a sub 3 plus, and then we're going to keep adding up until we get up to the value of n. So from our definition, it's abstract, we're going up to n, but when we do examples, you'll have a number that it will go up to. Okay, where, so I'll give you the names for each of these different pieces. I is the index of summation. So we just have some vocabulary here. Index of summation. N is the upper limit of summation. And in this case, the number 1, whatever that number is that we're starting at, is the lower limit of summation. Alright, so let's take a look at an example and see how we're going to use this. Again, it's called summation notation because we're going to be adding things up. So, example, find each sum. So for part A, we have the sum as I goes from 1 to 5 of 3i. And we could change the variable. In this example we're using I. In other examples we may use n or t or s. It doesn't really matter. So what this notation says is take the numbers from 1 to 5 and plug them into this expression and then add up all those terms. So plug in 1 first, so I have 3 times 1. Plug in 2 next, so I have 3 times 2. Plug in 3, so I have 3 times 3. Plug in 4, 3 times 4, and then our last value, 3 times 5. So we've got 3 plus 6 plus 9 plus 12 plus 15, which is going to equal 45. So the sum of 3i as I goes from 1 to 5 is 45. So some things to keep in mind here. I want to distinguish the difference between two things. So keep in mind, number 1 is that the first 5 terms of the sequence are 3, 6, 9, 12, and 15. but the sum of the first 5, scoot that up a little bit, sum of the first 5 terms is 45. So make sure you're reading the problems carefully so you know whether I just want a list of the first 5 terms or if we want the sum of the first 5 terms. Alright, let's try another example. Part B, I want the sum as k goes from 3 to 6 of 1 plus k squared. So notice this time we're not starting at 1, we're starting at 3, and I'm using a different variable, I'm using k. So I'm going to plug the numbers 3, 4, 5, and 6 in for k, figure out what those expressions are, and then add them all up. So first term is going to be 1 plus 3 squared plus, now I'm going to plug in 4, 1 plus 4 squared, plug in 5, 1 plus 5 squared, plug in 6, 1 plus 6 squared. So over here I've got 10 plus 17 plus 26 plus 37, and that gives us 90. Alright, next example. Feel free to pause the video after I write the problem down and see if you can figure it out, and then resume to see if you figured it out correctly. So I've got the sum as I goes from 1 to infinity. So this one's a little tricky. Of 3 over 10 raised to the I. So we're going to start at 1, we're going to plug in every number up to infinity. Obviously we're not going to plug in every single number up to infinity, but let's see what happens. So I have 3 over 10 to the first, plus 3 over 10 to the second, plus 3 over 10 to the third, plus 3 over 10 to the fourth, plus, and then we're going to keep going forever. But notice as the number that we substitute in gets larger and the denominator gets larger, what's happening to these fractions? As the denominator gets larger, the fractions are actually getting smaller. So we're getting a smaller and smaller number each time. So we've got 3 tenths plus 3 100ths plus 3 1,000ths plus 3 10,000ths, and then we're going to keep going. So if we look at these in terms of decimals, we've got 0.3 plus 0.03, and if you want these as decimals, just plug them into your calculator, plus 0.003 plus 0.0003 plus, and we're going to keep going on forever, so we're going to end up with 0.33333. Keep going. It's just going to add another 3 each time. So essentially, when we add this up to infinity, we're going to get 1/3. Alright, let me slide that up a little bit so you can see the last line. Okay, so there's 3 examples using summation. Let's move on to an example that uses a summation formula, but in a little different way. So we've got a $5,000 deposit, earns 3% interest, compounded quarterly. And we'll talk about what that means in a minute. The balance after n years is given by a sub n is equal to 5,000 times 1 plus 0.03 divided by 4 times n, where n is equal to 0, 1, 2, 3, etc. Okay, so notice some of the numbers in the problem. The 5,000 is over here. That's our principal. The interest, 3%, is over here. That's 0.03. It's compounded quarterly, so that's 4 times a year. That's why our interest is divided by 4. And n is going to be the number of years. So for part A, we want to find the first 3 terms. So basically what we're going to be finding is how much money will there be after year 0, so initially year 1 and year 2. So we're going to start by plugging in 0. Again, the n over here in the problem, they told us where to start. So a sub 0 is going to be 5,000 times 1 plus 0.03 divided by 4 raised to the 0. So go ahead and plug all this into your calculator. Hopefully you'll get 5,000. A sub 1, that's our next value of n to plug in. We have 5,000 times 1 plus 0.03 divided by 4 raised to the first. Plugging that into the calculator, we should have $5,037.50. And note, since we're compounding quarterly, that's 4 times a year, this is after 3 months. And then a sub 2, so that's after the second time that it's compounded, so that would be after 6 months. So we have 5,000 times 1 plus 0.03 divided by 4 raised to the second. And if you plug that into your calculator correctly, that should give you $5,075.28. And again, this is after 2 compounding periods, so that's after 6 months. Alright, so we're getting close on time. We have one more part of this problem to do. So for part B of this, part B, find the value of your investment after 10 years. So for 10 years, if we're compounding every quarter, so every 3 months, so 4 times a year, how many times will we be compounding our interest in 10 years? So 4 times per year for 10 years. That's 40 times getting interest. Okay, so that means, basically what that's telling us is that n is equal to 40. So we've got a sub 40. So again, that's going to be after 10 years, compounding 4 times a year. It's going to be 5,000 times 1 plus 0.03 divided by 4 raised to the 40th. And check yourself that you can plug this into the calculator correctly. That's $6,741.74. So 10 years, you've basically made about $1,741. Good investment, bad investment, not sure. As always, write down any questions that you have in the notes, and feel free to ask them during class tomorrow.